Log on, tune in, find out. Another good idea from Cambridge.
Welcome Jeremie Guilhot from the University of Sydney, who will tell us about Kazhdan-Lusztig cells and affine Weyl groups.
Thank you, and thank you very much for the invitation. I'm very pleased to be here today. So, first I will start with a little historical background on cells. So it first appears in a combinatorial setting, more precisely via the Robinson-Stansted correspondence. So as you probably all know, there is a 1-1 correspondence between the element of a symmetric group Sn and a pair of standard tableaux. So a cell, it was not called like that this time, but a cell is the set of elements which correspond to the pairs PQ with P fixed. And so the number of elements in a cell is the dimension of some irreducible in Sn. Later on, Joseph defined cells for an arbitrary Weyl group using primitive ideals in the enveloping algebra of a complex semi-simple Lie algebra. Then, in this setting, every left cell is a basis of a representation of W, where W is a Weyl group. Later on, in 1979, when Kazhdan and Lusztig defined cells for an arbitrary Coxeter group, and then each left cells give rise to a representation of the Coxeter group, but also to the Hecke algebra associated to it. And there is a geometric interpretation in terms of an intersection cohomology. Of course, the definition of Kazhdan-Lusztig coincides with the definition of Joseph's and with the Robinson-Stansted correspondence as well. And then Lusztig defines cells in the multi-parameter case, where you're allowed to put different weight on the generators of the Coxeter group. He formulated 15 conjecture. I'll came back to that later on. And there is as well a conjectural interpretation in terms of a character shifts on disconnected group. All right. So next, I'm just going to say some things about Coxeter groups. So a Coxeter group is a group generated by a set S and with relations of this form. The product of two generators SS prime is of order MSS prime, which is greater than 2, and each generator is of order 2. So in fact, every Coxeter group is a reflection group in some sense. If you take a vector space with basis indexed by the element of a capital S, and you define a bilinear form B with this formula, B of ES prime is minus cos of pi over the order of SS prime, then you can realize the Coxeter group as a reflection group where a reflection, sigma S, sends x to x minus 2b x ES. So as you can see, B of ES is equal to 1. So sigma S of ES is equal to minus ES, and then sigma S stabilizes the hyperplane orthogonal to ES with respect to this form, B. Now if B is positive definite, then V is an Euclidean space, and W is a finite reflection group, as we know them. Now, if we call a Coxeter group tame if the form B is positive, and integral if the MSS prime take the value in 2, 3, 4, 6, or infinity. There is mainly three types of a tame Coxeter group. So the finite, and integral when B is positively finite. These are the Weyl groups I was speaking about before. Then the finite and non-integral, so for example the diagonal group of order 5 or 10, depends what people say, but see what I mean. H3 and H4 as well. And then the infinite Coxeter group, and then the automatically integral, and the form B is only positive and not positively finite. These groups are the affine Weyl groups. As we will see later on as well, there's a strong relation between Weyl groups and affine Weyl groups. Okay. So now I can start with the definition of Kazhdan-Lusztig bases and cells. So you take a Coxeter group with generating set S and the usual long function. So the long function is you take an element of a Coxeter group. The length of W is just the minimal integer n such that W can be written as a product of n generators. But we want to work in the multi-parameter case. So a weight function is a function from W to n, which only satisfies the weight of W prime is the weight of W plus the weight of W prime as far as the length adds. So the first thing I can say with this definition is that, well, the length function is a weight function, obviously. So this is known as the equal parameter case. Next thing is that the weight function is completely determined by its value on capital S. Well, you just take an element W in your group, you write it as a product of n generators when n is the length of W, and then the weight of W has to be the sum of the weight of the Si. So taking a weight function of W or fixing some weight on the generators is the same thing. But for everything to work well, you need as well that the weight of S and equal the weight of T if S and T are conjugate. All right, so I have a Coxeter group, a generating set, and a weight function. Now I can associate the Weyl algebra over the ring of a Laurent polynomial in V. So this is an A3 algebra with basis indexed by the element of a Coxeter group. And the multiplication is given by this rule. TSTW, if the length goes up, SW, then it's just TSW. And if the length goes down, you have this term coming on. So if you put V equal to 1, this term goes away, and you just end up with the group algebra of W. So it's just a deformation of the group algebra. So on H, you can define a unique involution, which take V to V minus 1, and TW to TW minus 1 minus 1. So, well, it's just an element of the algebra is something like that. And you apply bar, you just apply it to everything works well. The TS are invertible, so things fine. And is this?
I'm not sure.
Yeah. Well, maybe I could just get rid of it. Anyway, so in 79, this Kazhdan-Lusztig defined a basis of H, the Kazhdan-Lusztig basis, and in 83, Lusztig did it for the unequal parameter case with a weight function. So you say that for any element of your group, there exists a unique element of H, which is stable under this involution, and such that when you write it in the standard basis, the TW, CW is equal to W plus a combination of Ty, and the coefficient, the Kazhdan-Lusztig polynomial, only involves strictly negative power of V. Then, since the length here of W is strictly less than LW, the CW form a basis of H, known as the Kazhdan-Lusztig basis. So as an example, C1 is just equal to T1, which is the identity element of the Hecke algebra. 1 is the identity of the Coxeter group. It's not very interesting, but if you take CS, then TS plus V to the power minus of the weight of ST1, then you can check it is stable under the bar involution. It can be written under this form, so this is the element CS. So that's the weight function there. Everything I'm saying depends on your choice of weight function. If you change the weight function, you don't get the same basis here. So I have Hecke algebra, a standard basis TW, the Kazhdan-Lusztig basis, the change of basis triangular, and the coefficient arising are Kazhdan-Lusztig polynomial. So using this new basis, you can define a left order relation saying that x is less or equal to y in the left order if the x appears in HCy for some h. So you just take an h in your algebra, multiply, so in which way did I write it? Cy. You decompose it again on the Kazhdan-Lusztig basis, and then if Cx appears in this sum, then x is less or equal to y. From there, you can define an equivalence relation, saying that x is equivalent to y in the left order if and only if x is less or equal to y and y less or equal to x. And the equivalence relation, the equivalence classes are called left cells of W. When I multiplied on the left there, but I can define the same thing multiplying on the right, so you get right cells. And then you can multiply on both sides, and you get two-sided cells. But you don't multiply it by necessarily by the same element on the left and on the right. You can choose H, C, Y, H prime. So the relation between left cells and right cells is like if X is less or equal to Y in the left order, it's equivalent to say that X minus 1 is less or equal to Y minus 1 in the right order. So if you know the left cells, well, you know the right cells. So, to sum up, if you take a W, you multiply on the left by H, you end up with a sum of Cy, where Y is less or equal to W in the left order. Same for right and two-sided, and you can decompose W as a disjust unit of left cells, right cells, and two-sided cells. Now, maybe I just start here again. If you take gamma to be a left cell of W, and you set E gamma to be the A span of the CW, the CY, such that Y is less or equal to W in the left order, and W lie in the left cell gamma, then E gamma hat to be the A span of the same thing, except now you ask Y doesn't lie in the left cell gamma, then both these things are left ideals of H using this thing. And so the quotient, which is noted like that, is naturally a left module of your Ecker algebra. So to each left cell, you can associate a left module by this. And it has a basis indexed by the element of the cells. You take all the things which are less or equal to W in the left order, and you take off the one which are strictly less than W in the left order. And you end up with a left module. Another thing I forgot to say, maybe I write it there, but if you take S in the generating set, W in W, then you always have the length of SW strictly bigger than the length of W. Then if you multiply CS and CW, you end up with always with CSW and something. So that you will always have, if SW, the length of SW is bigger than W, you will always have SW L less or equal to W in the left order. So let's just do a little example to clarify things a bit. Take W to be the Weyl group of type G2, though generated by S and T, and the three edges here means that the product ST is of order 6. You fix a weight for S, A in N, and the weight of T to be B. So first assume that A is strictly bigger than B. So the identity element and the longest element are always left cells, two-sided cell and things for some reasons. So if you multiplied these two things, then there is a CS appearing there. So if I use the definition, this tells me that S is less or equal to, which one is it? TS in the left order. But on the other hand, TS is less or equal to S in the left order using this relation. You just have S, which is bigger than TS, bigger than STS, bigger than TS. And so this thing is included in a left cell. Then if you keep doing some computation, you can show that this is actually a left cell. There's nothing else in there. Well, you can do the same thing with some other element. Here you have ST, which is less or equal to TS, TST, and you get this is a left cell. and the last two things are left cells on their own. Now, if you do the same thing when A equal B, if I compute the same product, and well, you get this partition into cells, but this product here, now it's only that. So if I change the weight function, everything is changing. You don't have the same partition into cells, and the product of the Kazhdan-Lusztig base is not the same. And when A is strictly smaller than B, well, this is symmetric, so you just have to replace the T by the S, and you get the partition into cells. And if you do, again, the same product, then you only get this. So everything depends on the weight function in a non-trivial, highly non-trivial way, I should say. All right. So now you can define the structure constant associated to the Kazhdan-Lusztig basis, which is just you multiply two elements of the basis and you decompose it again on the basis. So using that, I can give you a little bit more information of this cells, of this cell module. Like if so, let's try to take the same notation. Y. You take Y in gamma and X in W. So the element of the Kazhdan-Lusztig basis will act on this module this way. It will be the sum. So here you will have the structure constant coming up. But it's not the sum of all on all Z, but you just have to stay in the cell. So you just take the sum for the Z in gamma. So this is the action of a Kazhdan-Lusztig basis. So using that, like Lusztig defined the A function. So the A function of Z, you look at all this polynomial h, x, y, z with a fixed z. You look at all the power of v which appears in such polynomial. You take the highest one, and then you get the A function. Well, it's not even clear, but it is well defined. Like if your group is infinite, you may have like as high power of v as you want in such polynomials. In fact, there's a conjecture which says that it should be well defined for any groups, but it's at least true for affine Weyl groups. Anyway, using this like with this A function, the 15 conjecture, the conjecture I was speaking about at the beginning. So for example, if x is equivalent to y in the two-sided order, then x and y should have the same A function. If x is less or equal to y in the two-sided order and they have the same A function, then they should be equivalent. And if x is less or equal to y in the left order and they are equivalent in the two-sided order, then they should be left equivalent. So I told you that if you know the left cells, you know the right cells. However, if you know the left cell and the right cells, you don't know the two-sided cells in general. And there's plenty of examples where it's really hard to compute the two-sided cell, even if you know the left and the right cell. But if you believe in this conjecture, then if you know the left cells, you know the two-sided cell, because this thing implies that the two-sided cells, which be the smallest subset of W, which are at the same time union of left cells and union of right cells. So I should mention as well that this A function is actually extremely hard to compute, even in small groups. Well, the example I gave you before, you can do it by hand, but like when the group is getting a bit bigger, it's really hard to compute. Okay, so in the example I gave you in the group G2, we've seen that the partition is changing when the weight function, when you change the parameters. So now I'm going to just explain a conjecture of Bonafé which like describe how this thing works in a general setting. So you take a Coxeter group, as usual, a generating set S. You assume that S is a disjoint union on S1 and S2, and that no element of S1 is conjugate to an element of S2. This way, I can fix a weight function taking any value on S1 and another value on S2. Since they are not conjugate, they can be different. I can have two parameters. So I'll denote the weight function which take the value A on S1 by LAB and B on S2. And the partition into cells associated to this weight function, I denote it by curly L, is that right? Yeah, curly L of AB of W. this is the partition of W with respect to this weight function. So the first part of the semi-continuity conjecture of Bonafé tells you that it exists a finite number of rational number such that if you take two parameters a, b, and two different parameters a prime, b prime, such that the ratio is in between Ri and Ri plus 1, then the partition of two cells should be the same. Now, when a over b equal Ri, you should be able to find the partition with these parameters just looking at the partition when a over b is strictly smaller than Ri, and when a prime b prime is strictly bigger than Ri. You look at the partition on the left, at the partition of the right, you take the smallest common refinement of these two, and you should obtain the partition at this thing. So if W is finite, the first part of this conjecture is clear. You have a finite number of elements, you have a finite number of different decompositions, so obviously you will find such rational number. But like if W is infinite, then already it's a hard question. You have an infinite group, you should be able, like, why don't you get like an infinite number of partitions? And then this is another. All right, so if I go back to the example I gave you, what does it say? All right, we had W of type G2. We had these two decomposition for A strictly bigger than B and A strictly smaller than B. So in this case, actually, there's only one rational number, which is 1. So the smallest common refinement of these two things, well, one is a cell up there and down there, so it should be a cell in A equal B case. This one as well. Now, T is alone there, but T is with ST here, and this guy is alone here, but is in the other there. So this whole thing should be a cells. That's why I like to take the smallest common refinement, and these two, well, the same. They have to get together. And this is actually the partition in the case A equal B. So it works for at least G2. So the second part of the semi-continuity conjecture deals with what we call the asymptotic case, when one of the parameters is much bigger than the other, and when one of the parameters is equal to 0. So remember, S is a union of S1, S2. I consider now the weight function of W, which take value A on S1 and value 0 on S2. And I'm looking at the decomposition of W with this weight function. So it should be the smallest subset, which are union of left cells for weight function L of AB, where A is much bigger than B. And as well, it should be stable by multiplication by the group generated by S2, which is the generators of weight 0. So I could be a bit more precise here. I can give actually a nice description of the cells with respect to the weight function LA0. So you fix S1 to be the set of conjugate of a generator in S1 by the element in S2, so the WTW1. This set is generating a subgroup of W, which we know W tilde. And it turns out that actually W tilde S1 tilde is a Coxeter group. It has been proved by Gall, and then later on by Bonafé and Dyer. So this thing, it's not an easy fact, like this thing is a Coxeter group. And then W can be written as the semi-direct product of WS2 times this W tilde. Now, on this W tilde, you can put a weight function on it, which is L tilde. The weight of WTW1 will be just the weight of T, so here it's going to be A. And so, first thing you can say is the weight function L tilde takes only positive value on W tilde. And now the cells of W with respect to this weight function should be of this form. The left cell should be, you take a left cell of W tilde, L tilde, so this weight function and this group, multiply on the left by WS2, it should be a left cell of W, then the right cell obviously multiplying on the right, and the two-sided cell multiplying on both sides. But let's take. Yep. The what? I don't know, to be honest. Yeah. It should be. Can I erase now? Right. So, 1 is a cell, is always a cell of W tilde. So if I look at this thing, well, then WS2 should be a union of cell for W when A is much bigger than B. All right, so I'm saying that like if you have to go back to the conjecture, you take the cells of W with respect to this weight function are of this form. Then 1 is always a cells of W tilde. So the first part tells you that WS2 times 1, which is just WS2, should be a cell of W with respect to the weight function L of AB, where A is much bigger than B. Then it should be as well a union of right cell and a union of two-sided cell, if you put C equal to 1 there. In fact, this is true. In general, if you take a Coxeter group with one parameter much bigger than the other, then the group generated by the generators of weight B, of lightweight, considered as a proper Coxeter group, then these cells stay cells in the big group. So this is an evidence for the semi-continuity conjecture in the asymptotic case. So the semi-continuity conjecture is known to hold for dihedral groups, which has been done by Geck-Pfeiffer in the finite case and Lustig in the infinite case. For type F4 by Geck, these two cases are just like explicit computation. As we will see later on, it holds for affine Weyl groups of rank 2. And maybe I should mention that it fits with plenty of conjecture we have in type Bn. All right, so this is for the. Now I'm going to turn my attention to affine Weyl groups in particular. So I just give you a quick, like the classification of all irreducible affine Weyl groups, which just means like the vertices are the generators. If they are linked by one thing, then the product is of order 3, 2 order 4, 3 order 6, and they're infinity order. So, well, for example, in type AN tilde, you will never have unequal parameters because this thing is conjugate to this one, they must have same weight. You go all around, everything must have the same weight. So unequal parameters only arise in this case here. And another thing which is nice with reducible affine Weyl groups is that all proper parabolic subgroups are finite. Or you could check it by hand, take all the things, they're all finite. So I want to give a geometric presentation, which is nice to work with cells. So you start with a root system of a Weyl group. And of a Weyl group W0, and you draw all the hyperplane with equation. So you're in a Euclidean space here of order 2, sorry, not 0, equal k. So you get, if you use these roots, you get all this hyperplane, and you keep going. You end up with this picture. An alcove is a connected component of the space minus all the hyperplanes, so any triangle there. You fix an alcove A0, any one, this one. And so the faces of an alcove are the codimension 1 facets. So it's just like the side of the triangle. So here you have 3 faces. And now you look at the orbit of these faces under the action of all the orthogonal reflection. So if you start with the red, well here, if I do there, and you do it for everywhere. Then the green and the blue. And in fact, doing these 3, you cover every faces of every alcove on your plan. So we have 3 orbits, the green, the red, and the blue. And then for any S in this set of orbits, you can define an involution of alcoves where S take A to SA, where SA is the only alcove which share with A a face of type S. And you look at the group generated by all such maps, and you end up with a Coxeter group, W. Well, of course, here I've started with the root system of G2, so I will end up with the affine Weyl group of type G2. But we'll see that afterwards. So just to clarify a bit, I'll just give you an example of this action. So we identify for any element like of this group generated by all these things, we associate the alcove W of A0. So how do I compute W of A0? So I have A0 and I want to apply this thing. S3 of A0 is the unique alcove which share with A0 a face of type S3, so a blue face. There's only one there. And then you apply a red thing, so you look at the only alcove which share with this one, a red face. You have to go there, and then you apply a green one, so you cross a green, then a red, and then a blue. So here, in my example, I started with the Weyl group of type G2. I just want to show you that you really end up with the affine Weyl group of type G2, which is like that. Name. Well, what happens if you applied S1 and S2? So this is red and green, so you're just going to make a tour around the identity. And you go back to the identity, so S1 and S2 is of order 6. Now, if you apply the red and blue, well, you do a tour, but just around this point. So this is the 2 generators of all the product is of order 3, and then the last 2 commutes. So it's just the thing you make a tour here. Yeah, the other thing you need later on is like if you take an hyperplane and if it supports a face of type S and a face of type T, then S and T are conjugate. So here S1 is conjugate to no other element. So if you look at the hyperplane of type S1, which are the green one, when they're all green. But if you look at the hyperplane of type S2 blue, then S2 and N3 are conjugate, so you can have both color on one hyperplane, red and blue. So you can associate to any hyperplane a weight, the weight of the faces it contains. All right, so my aim here still is to decompose an affine Weyl group in cells. The main problem is that like an affine Weyl group is infinite. So the first thing to do is to deal with that. So I'm just going to speak about like translation. They have nice property. Well, maybe I should say, yeah, with this presentation, the length of an element is equal to the number of hyperplanes which separate the alcove A0 and the alcove W of A0. So I take a translation. The translation is just an alcove such that if you apply it to A0, then you get a translate of A0. So if I take U1 here, well, it takes A0 to there, which is a translate. So if I look at the set of hyperplane which separate these 2 alcoves, they're there. So why does the length of W is equal to the number of hyperplane. Well, you want to go from this to A0 to the yellow one. You're only allowed to cross one hyperplane at a time, and you want to do it with the less possible generators. So you just cross the one which separates both of them. Now, I'm looking at the Z, all the Z in W, such that, well, Z.U1, I should have defined that. So I write something Z.U1 if and only if the length of ZU1 is equal to the length of Z plus the length of U1. And I wonder where, if I apply Z to U1, where my alcove ZU1 the A0 will be, of A0 will be. So I apply U1, I'm there. Now I apply a Z, and I don't want the length to go down. So in fact, I'm not allowed to cross any of this red hyperplane. If I cross one, then the length will go down because it's the number of hyperplanes separating this thing. So if the length of ZU1 is length of Z plus length of U1, the alcove Z of U1 to A0 has to be there. Now I'm looking at the orbit of this translation with like all the hyperplane going through 0. So I have 6 of them. And I do the same thing for each of these translation. So this one takes the alcove A0 there. I look at this set, the set of Z which like such that the length adds, and you do that for everything. So there are these joints. It doesn't, like for example, well, what can you say? If two elements ZUI to the power R and Z prime UJ to the power R plus M are equal, then they have to be in the same zone. Of course, this one is there, like this one has to be somewhere else, but they're equal, so everything has to be equal. The I has to be equal to J and Z equal to Z prime UJ to the power of M. And maybe it doesn't seem like a very strong result like that, but if you keep like using such rules, then you can show that the Kazhdan-Lusztig polynomial are invariant by translation, by, well, to be completely honest, by long enough translation. So you take any affine Weyl group, you take a translation in it, you look at all this UI, the orbit like that, and then you have, if R is large enough, then the Kazhdan-Lusztig polynomial are invariant. So this is, using this, you can deal with the fact that the affine Weyl group is infinite. And well, I say it's come from there. Well, if you look, actually what you do is you take this Breuer interval, I didn't define it, but you can show that for R large enough, this Breuer interval is isomorphic to this one, using such kind of thing.
Was this previously known in the equal parameter case?
Yeah, it was known, it was proved by Lusztig in the equal parameter case. But not in the same way. All right, so using these kind of things, I've been able to find a partition into cells of all of the affine Weyl group of rank 2, so G2 tilde and B2 tilde. Here there is 3 parameters. And actually the methods involved in this thing allows me as well to check one of the Lusztig conjecture. Because one can get like all the left order on the left cells, so you can check this thing. So as I say, what do we use to prove this thing? Well, first of all, the invariance of the Kazhdan-Lusztig polynomials. This allows you to say, well, this set is included in a left cell. Because you can use the invariance by translation to show that it is infinite sets are included in left cells. Then, maybe I should have put that third point, so let's go directly to the third point. Then there is a generalized induction theorem, which you can apply to any Coxeter group. And this thing allows you to separate cells. It's like the main tool to say, well, this set is a union of cells. So if you combine 1 and 2, you say, well, it's included in a left cells, then it's a union of cells, so it has to be a left cells. And you keep doing things like that, then you can get this thing. And the other thing I've used is the determination of the lowest two-sided cells for all affine Weyl groups. And this is quite handy because the lowest two-sided cell, if I have time, I'll give a word about that afterwards, is the biggest one. It contains nearly all the elements, so you find already plenty of left cells. All right, so instead of giving you like all the partition, which I don't have time, well, in case of B2 tilde, I think there is like 25 or 30 different decomposition. I just give you an example of a way to find a partition of you take any affine Weyl group, and a way to find a partition into cells, just looking at the cells of a parabolic subgroup, which are finite. I just give an example. So you start G2 tilde with this parameter, A is strictly bigger than 3B, and you look at the two-sided cell in the of the parabolic subgroups. So you have this one. I gave you the partition before as an example. You have A2, and you have S1, S3, which commute. So if you decompose all this group in cells, that's what you get. This is the identity. This is the longest element in S1, S2. This is, well, the cells I found before. So this is just the partition. Two elements have the same color if they lie in the same two-sided cells. So here, well, it's fine. The parabolic subgroup are finite and quite small, so I know all these things. And I put the value of the A function on the right. So you start with the highest A function, the two-sided cell with the highest A function, which is W12, the longest element in S1, S2. And you define B0 tilde to be the set of W, such that W can be written X, U, Y, and the length as. The length of W is the sum of length of X plus length of U plus length of Y. This should give you a cell. Well, if I fix Y to be 1, then I'm looking at all the elements. Maybe I erase that just to show you find it in the. So what does this look like? And I want the length to X W12 to be the length of X plus the length W12. Well, first, you apply W12. So you start from A0, you do a tour, you arrive here. And now you want to look at all the things such that the length adds. Well, you cross this hyperplane, so you're not allowed to cross it again. And you cross this one, so you're not allowed to cross it again either. So you get this thing. The yellow is not so beautiful, I'm afraid. Now, if you apply first S3, then you do the. All right, maybe I should write it down. It's XW12 S3. So you apply S3, you end up here. Then you apply W12, you make a tour, and then everything which adds cannot cross these two hyperplanes. You end up there, and you keep doing that for all the elements of your group. So this is actually the lowest two-sided cell, and this thing works for any affine Weyl group. You take the longest element of a Weyl group lying in the affine Weyl group, and you define such a set, and this is always the lowest two-sided cell. And each of these things is a left cell. Okay, then you keep going. You take B1, you define it the same way, except you take off all the things which are already taken in B0. So it's S1, S2, S1, so you start from the black one, you end up in the blue, and everything which adds and doesn't lie in B0 tilde gives you this set. And you keep doing that for all the group. You end up with these blue things. And now you do it with W13, which is here. It gives you this one, everything. And you keep going like that. And you end up with the partition of your affine Weyl group into cells. All right, so at least this thing works for this way of finding the partition for an affine Weyl group. Works for a G2 tilde and B2 tilde for any parameters. But if you assume plenty of Lusztig conjecture, then you can show that it's true for any affine Weyl group. But actually, it's based on this. It's based on P1, P15, some over the connectedness of cells, but as well this phi. You take a W in your group, you define the set ZW. So this thing consists of all the U in W such that U lie in a parabolic subgroup, strict. W can be written X, U, Y, and the length of W is equal to the length of X, length of U, plus length of Y. And actually, Lusztig conjecture, if you put A prime W to be the max of the A function of such U for all U in this set, then Lusztig conjecture then A prime of W should be the A function of W. And what I'm doing here is basically, the idea is just like in yellow, it's like all the thing with A prime function equal to 3A plus 3B, and just characterizing this kind of thing. All right. So now I just want to say a word about the asymptotic case in the affine case. So again, G2, L of S1 equal A, strictly positive, and the weight of S2 equals 0. So in this case, you can write W. So you look at the action of S2, S3 on S1, you get three elements, S1, S2, S1, S2, and this one. And you can show that these three things generate an affine Weyl group of type A2 tilde. So how do I see that on the picture? Well, you just look at the hyperplane, which have weight A, strictly positive. So if you remember, I told you that like they all have the same, like the hyperplane which contain a face of type S1 have all the same color. So this is all the hyperplane containing a face of type S1. Well, if I apply S1, so this is the group generated by S2, S3, all these alcoves. If I apply S1, I end up there, and then multiply on the left by WS2, 3, give me this thing. S2, S1, S2 is here, multiplying by WS2, S3. And so you see where I go. These three things send you either here, there, or there. And so you get like you can picture W tilde as the group generated, the affine Weyl group associated to this hyperplane, generated by all the orthogonal reflection, this big hyperplane. And so the decomposition into cells of W with respect to this weight function is the partition of W tilde in cells times WS2, S3. So this is the partition of A2 tilde. It was proved by Lusztig. And that's the partition of G2 tilde for such parameters. Okay, so the two-sided cells are the things, are the alcoves with same colors, and then the left cells are the connected such cells. All the connected yellow set are left cells. So if I do what I did before for all parameters in G2 tilde. So this is the partition when B equals 0, and then the partition when A over B is strictly bigger than 2. Okay, so what does the semi-continuity conjecture was telling me? Well, the cells, so in this case, should be the smallest subset, such that there are union of cells for this case, and stable by multiplication by WS2, S3. Well, this red one is here, like this red one and the green one, but here this is a triangle. Here you have WS2, S3, so these two things, if you want it to be stable by multiplication by S2, S3, they have to be in the same cell. And obviously they get in the same cell. And you can do that for everything, so the theorem I told you is that this group is always a union of cell. Well, everything fits with the conjecture. All right, next you have to look at A over B equal 2. Well, nothing very big happened. The only thing is that this green cells is now light green. So why does it happen like that? Well, because the dark green there was S2, S3 corresponding to the element S3, S2, S3. The function of this thing is 3B. And now the light green one was associated to S1, S3. And the function of S1, S3 is like A plus B. So what does happen when A over B equal 2? Well, these two A functions are equal. And so this dark green one is getting with the light green. And then you keep going. You get this. This one were green. Now they're light blue, and they're going into the blue. So here, just only this one is moving. Then the equal parameter case, which was proved by Lusztig, this picture, and on the other side. So it's the same. You have this partition for A over B is strictly bigger than 1. This partition for A over B is strictly smaller than 1. And then the partition for A over B equal 1 has to be this one, because it's the smallest common refinement such that it is union of left cells on both sides. And finally, the other asymptotic case, which is A equals 0 and B is strictly bigger than 0. So this time, I just look at the hyperplane which contain the faces of type S2 or S3. I look at the affine Weyl group generated by such orthogonal reflection. Again, I end up with an affine Weyl group of type A2, but not exactly realized in the same way. This is S1, identity and S1, and it fits. It's not as obvious as in the first case, but like the semi-continuity conjecture holds here as well. So I could have done that with B2 tilde, but it's, as I said, much longer. All right, so I'm going to stop here. Thank you.
Any questions?
So, if you take Hofstadter group and take all the different Hecke algebras with different weight functions, then the structure of cells will be very different.
Yeah.
But if you then specialize T back to 1, you will get different Kazhdan-Lusztig bases with the ordinary group algebra, or will they all specialize to the same thing?
Sorry, I don't know.
Interesting.
Yeah.
Is there some kind of semi-continuity statement for, well, for B2 tilde or for Cn tilde, where you have 3 parameters?
Yeah. It's actually, yeah, I only give, maybe I should have mentioned it, I only get the simple version with 2 parameters, because when you get with 3 parameters, it gets a bit more complicated, but exactly the same thing happens.
Okay, so then the statement is that there's some collection of planes in R3.
There's a collection of hyperplane, which we like, the essential hyperplane is when the partition is moving, and then when you have 3 parameters, obviously, yeah,
Okay.
same thing.
Any other questions? Let's thank the speaker again.